Hello everyone, welcome to my channel. In this video, we'll be discussing about properties of cardiac muscle. So this is also very important topic in cardiovascular physiology. So in this video, I'll be explaining this topic with the help of these notes so that you can have an idea whenever this question is being asked in exam, how you have to perform, right? Because this is the major mistake done by students. They don't know how to perform this question, right? So mostly you'll get some videos or you'll get material in books explaining these three properties when we talk about cardiac muscle properties, right? So we should have a clear picture whenever we talk about properties of cardiac muscle. What are those properties? Okay, so properties of cardiac muscles are basically divided in four categories. One is the morphological property. So this basically tells about the structural component of cardiac muscle, which makes it different from skeletal muscle, right? Then are electrical properties and mechanical properties, which we often explain in all the videos approx and all the study material. But again, we don't know how to explain these, right? Just giving definition of these component will not give good marks, right? So in this video we'll be looking toward how to explain properly whenever this question is being asked in examination. So morphological properties, electrical properties, mechanical properties and metabolic properties, right? So obviously these are two major components, but rest we should know. We should at least a little bit will touch upon this topic also. So starting with morphological properties. So what makes cardiac muscle different from skeletal muscle? When we if you have seen skeletal muscle, you know that these are cylindrical and striated muscles, skeletal muscle, right? But cardiac is striated but branched. Okay, if you see the structure of cardiac muscle, it's somehow like this. So the branching is present, but there are striations also present, right? And within these branches there is one nucleus present at center. Fine. The major peculiarities, so we have to target these components. Like this is striated, intercalated discs are present. If you can see these jet lines, there are intercalated discs and gap junctions are present, right? There is well developed sarcoplasmic reticulum, which also is very important, and there is one triad per sarcomere. So we should know a little bit about these details. So we know that first of all, if we see structure of this cardiac muscle and branching, so here we have gap junctions. Gap junctions are present. There is some space between two cells, because of which the ionic exchange can occur easily, right? So there are various cells which are ultimately communicating with each other with the help of this space provided, which is called gap junctions, right? Now, because of these gap junctions, whole atria and whole ventricle, they get depolarized at once, and because of this, they can contract as one unit, right? And this property is called syncytium. Syncytium of heart. Heart acts as syncytium. You can be asked in 2 marks why heart acts as syncytium. That's because of the gap junctions. Okay. So first is this property which is the basically importance of intercalated disc and gap junctions, right? Second thing is well developed SR, sarcoplasmic reticulum. If you remember cardiac muscle, skeletal muscle, there is T-tibble and there are SR, sarcoplasmic reticulum present over here. Okay, so we call this as triad, right? So in various books you will get that there are two triads in skeletal muscle, right? And there is one triad in cardiac muscle. But if you see closely, 1, 2, 3, these three things makes triad. Okay, but in cardiac muscle there is one SR is missing here. So one T-tubule and one SR. So it should be actually called as dyad, not triad, right? Dyad arrangement is present in cardiac muscle. Second thing, within this arrangement, the T-tubule in skeletal muscle is not so wide, but cardiac muscle have very wide T-tubule, right? And second thing, the sarcoplasmic reticulum is not well organized. In fact, it's sparsely organized like this. So here you know that there are DHPR and ryanodine receptor present. DHPR channel present in skeletal muscle and ryanodine receptor on SR, right? There is 1:2 channels present, but here there is 4:10 channel present when we talk about DHPR and dynodine. Why? Because that's why the SR is this arrangement is present over SR. So it keeps on rotating 90 degrees so that various ryanodine receptors, they can come in front of these four DHPR channel and it can continue beating, right? So this muscle, the cardiac muscle contraction, we know that it will have basically all over life heart has to contract, unlike skeletal muscle which basically contracts whenever needed only, right? So here we need more muscle contraction and continuous muscle contraction. That's why we have more channels present over here. And this SR is also organized in such a way that it keeps on rotating and various rest channel also come in contact with this DHPR, right? So these are some structural peculiarities which we should be knowing when we talk about properties of cardiac muscle. So this is all about morphological property of cardiac muscle. If you want to get deep knowledge about cardiac muscle, you can visit my cardiac muscle video, right? Coming to next property, which is electrical property. Okay, so in this video we'll be talking about electrical property, autorhythmicity, excitability and conductivity. So we'll discuss what we have to write in these three headings, right? Next is mechanical property, in which we'll be talking about refractory period, contractility property, hollow null, staircase phenomena and summation of subliminal stimuli. So these are the property which we should explain in detail whenever this question comes. But when we talk about metabolic property, you can actually leave this component if you want. But obviously this is a property of cardiac muscle because heart, the cardiac muscle, it needs energy for our whole life, right? So there will be obviously some specialties about the oxidative process, right? So blood supply is 80 ml per 100 gram per minute or 250 ml per minute blood flow is there, and numerous mitochondria are present which are basically our energy source, and high myoglobin content is present here and highly oxidative tissue. So anaerobic respiration is approximately, it's roughly 1 to 2% anaerobic oxidation occur in heart. Nutrients are basically the major energy sources fat here. Okay. So that is peculiarities of metabolic. Okay. Now we'll be talking about the major part of cardiac muscle properties, that is electrical property. Okay. So starting with the electrical properties. So first is autorhythmicity. Right. In last video, if you have seen, we have explained pacemaker potential and the action potential of cardiomyocyte. So if you have attended those two videos, you should be very clear about autorhythmicity and excitability property. So the same thing we have to explain here. So what is autorhythmicity? Autorhythmicity is ability to generate action potential on its own, right? In absence of any stimulus. Auto means by itself, right? So rhythm, it can generate its own rhythm. Fine. And we know very well that pacemaker, which is SA node present in heart, it can generate its own rhythm at highest rate. So obviously that will dominate, right? Whoever present, whoever can generate rhythm at highest rate, that tissue will be called as pacemaker, right? So action potential generated in SA node is called pacemaker potential. Now the cause of autorhythmicity is nothing but phase 4 of this action potential or pacemaker potential, and we call that phase 4 as pre-potential or slow depolarization, right? Which is due to funny currents and the calcium channels, right? If you remember, you can attend my last video also for this. So this is pacemaker potential, in which this part from this to this is the pre-potential. So because of this slow, the heart SA node is able to generate the next rhythm and with a proper spacing intervals. So that is the property of autorhythmicity. It can generate its own rhythm at a specific rhythm, at a specific rate, okay, and causes funny channels and transit calcium channels. Next is property of excitability. So we have seen that ability to generate action potential when there is no stimulus. So here cardiac muscle is excitable, but it gets the stimulus from the SA node. So that pacemaker potential is basically transferred to the cardiac tissues and then it causes basically action potential in response to a stimulus present, right? So cardiac muscle is produced, action potential is produced in response to pacemaker potential, which is conducted to whole muscle via conductive tissue, right? So this was the pacemaker potential, and it transferred via the gap junctions to all the tissues, and then the cardiac tissue have this much action potential. So this cardiac action potential you have to explain whenever this excitability property is being asked. Fine. So all the phases you can explain here in these two segments, and you can visit my videos for the explanation part of this, right? If you compare just phases, so this is a slow depolarization, this is fast depolarization phase. One phase which is because of potassium efflux, and then we have plateau, second phase because of potassium efflux and calcium influx, right? Simultaneously it was going, that's why it is plateau, no change in membrane potential. And then we have repolarization phase, 1 and 2 are missing in pacemaker potential, so 3 is same. And then we have 4 in pacemaker potential, but here we have stable RMP. So these are some differences of both the action potential. Okay, next property is conductivity. Now this is the third property, electrical property of cardiac muscle, conductivity, because there are some tissues which can generate their own rhythm, and there are some tissues we can be excitable in response to that, but in between there are some tissue which can conduct that action potential, right? So those are conductive tissue. So impulse in SA node is transmitted to atria and ventricles via conductive tissues, AV node, internodal fibers, bundle of His, and Purkinje fibers. So in our first video of cardiovascular system, when we talked about the functional anatomy of heart, we have discussed this part, conductive tissue of heart. So you can visit that for details here. But whenever being asked, you have to draw these fibers, and you have to tell that about some speed, conduction speed of these fibers and location only, right? So that will cover the conductivity part. Just for revision, if you see, SA node is present where the superior vena cava is basically touching the atria, right? It's meeting the atria part. So where SA node is present. SA node, then there are internodal fibers present. Okay, then we have AV node. AV node, from AV node there are left and right bundle of His, and then we have Purkinje fibers. So these are 4 conductive tissue. Okay, then so this was all about electrical properties. Now coming to mechanical properties of heart. So these properties are also very simple. If you have gone through amphibian physiology, this will be again very simple, right? So starting with refractory period. Mechanical properties are basically, so first is very important, which is refractory period. Refractory period is the period, is the duration when the muscle don't respond to any stimulus irrespective of its strength. Okay, so that is refractory period, means muscle is refractory to any stimulus, it will not respond. Duration of action potential in cardiac muscle is 250 to 300 millisecond. Duration of action potential, right? Hence, because of this long duration, muscle is also having this long refractory period. Okay, and this is the reason why cardiac muscle can't be tetanized. Okay, so what that means to you is we have cardiac action potential like this. So this is phase 0, this is 1, this is 2, this is 3, and this is 4, right? So this action potential duration is very long. If you will compare with skeletal muscle, it's around 2 to 5 millisecond, skeletal muscle. But here, if we talk about, it's around 250 to 300 millisecond. It's very long compared to skeletal muscle, right? So because of this long period, cardiac muscle we can be tetanized easily. What is tetanized basically? So whenever a muscle is contracted, right, it's relaxing. Again, it is stimulated. Obviously, it will not relax. Then it will again try to contract. Okay. If this keeps on repeating, there will be sustained contraction. This is called tetanus. Tetanus, right? Fine. So skeletal muscle, because of this very less duration of action potential, it can easily undergo another contractions, right? And this is the reason that muscle can be tetanized. But when we talk about cardiac muscle, this is very long period, right? From starting of third phase, which is repolarization, this part, This part is called absolute refractory period. What that means? Absolute refractory period is the period where if you stimulate this tissue with a stronger stimulus, stronger than whatever has been applied, stronger stimulus, right? It will not respond. It will be refractory to that stimulus. It will not respond. But for this duration, which is around 50 milliseconds, if you will stimulate here, okay, with stronger stimulus, mind it, stronger stimulus, so the stimulus strength will be more than the applied, right? So if you will stimulate here with stronger stimulus, you can excite the cardiac muscle here. This is called relative refractory period. Okay. So absolute refractory period when even strong stimulus can't excite a cardiac muscle. 250 to 300 millisecond is action potential, in which 180 to 200 millisecond is absolute refractory periods. Means from starting, this is because of from phase 0 till phase 2 or early part of phase 3 is the absolute refractory period. Then relative refractory period when if stronger stimulus is applied, the muscle can respond. Okay. So this was all about refractory period. Coming to next property, which is mechanical property of cardiac muscle, staircase phenomena. So what is staircase phenomena is successive increase in force of contraction of cardiac muscle if heart is stimulated repeatedly with threshold stimulus. Okay, so what is that basically? Here if you can see, this stimulus strength should be threshold, okay, because below threshold the muscle is not responsive, there are no response. Okay, so at threshold stimulus muscle is having this force of contraction. So if you give again repeated stimulus are given, every time the height of contraction keeps on increasing, and if you plot this height of contraction like this, it resembles a staircase. Okay, this is called staircase phenomenon. Fine. So basically what is happening, cause of staircase phenomena is nothing. If you have gone through amphibian physiology, you must be knowing what is beneficial effect. Beneficial effect, right? So the same property we are dealing with here. Because of this property we have done some experiment on amphibian, and then we came to know that there is beneficial effect, right? The same property is also applied to our heart muscle. So cause of beneficial is what? Basically second stimulus gets benefited because of first stimulus. Why? The first muscle is undergoing contraction, right? Then there are calcium present inside the muscle, so those calcium are not taken back into the muscle, but before that we are stimulating it again and more calcium is coming. So because of this, intracellularly there is increase in calcium concentration, and we know that higher the calcium, higher is force of contraction. It's directly proportional to calcium concentration, right? Second thing is there is reduced viscosity of muscle, resistance is less because of the previous contraction, right? There is high temperature because of previous contraction, and that because of all these reasons there is increase in force of contraction every time. So basically second stimulus gets benefited because of first stimulus, and that's why we call it as beneficial effect, right? So this phenomena which resemble a staircase is called staircase phenomena. Next property, which is mechanical property, is all or none law. Whenever we talk about contraction, it's mechanical, right? Whenever we talk about action potential, it's electrical property. So you don't have to be confused in these two terms, what is mechanical or electrical, right? All or none law, what is this? Basically on stimulation of cardiac muscle, muscle either don't contract, or if it contract, it does with maximal of its capacity. What that means? So whenever you stimulate a muscle, if it gives a response, it will be maximal. Okay, so every time you will get same force of contraction or same strength of contraction. Okay, so that is all or none law. Means either there will be no response. If there is response, muscle will contract to its maximum ability. All or none, right? So increase in stimulus strength does not increase force of contraction. If you will increase stimulus strength here, if you will increase the current stimulus, okay, even then the force of contraction is maximal at minimum strength, right? There will not be any change. Then comes his last property, which is summation of subliminal stimuli. Summation of subliminal stimuli, what is that basically? Subliminal stimuli is basically sub-threshold stimuli. What is sub-threshold stimuli? The strength of stimulus which is not able to elicit any response. So there were no responses. Okay, when we increase further stimulus, there was response. So that was threshold stimulus, right? Then these sub-threshold stimulus which are not able to elicit any response, whenever given together in large number, they are able to generate response. Okay, so that is called summation of the subliminal or sub-threshold stimuli, right? So when many sub-threshold stimuli given together, muscle can respond. So that property is called summation of subliminal stimuli. Now last property left is basically contractility property, and now you will comment which property it is. It is electrical property or mechanical property. You will tell me in comment box. So contractility, why it is important? In contractility, what we have to explain is basically the force of contraction. The force of contraction is basically directly proportional to initial length of muscle. What that means? So whenever you stretch that muscle, there is increase in force of contraction. Okay, but with this you have to write that within physiological limit. Within physiological limit. Why? Okay, so this law is called. This law was given by Frank and Starling. So we call them Frank-Starling law, that force of contraction is directly proportional to initial length of muscle fiber, okay, within physiological limit. What that means to you? If you draw a graph, on x-axis there is length, and on y-axis there is tension, or we call them force of contraction, right? So if you draw length tension relationship graph and you will stretch that muscle, so here length is increasing, means you are stretching that muscle. So at starting, what happens is when you increase length, there is increasing tension. Fine, directly proportional. What we are talking about here, force is directly proportional to initial length. So when length is stretched, muscle is stretched, there is increase in length, increase in tension, but till a limit. After that, what happens? There is somehow plateau. This is maximal. Okay, then there is drop in the tension. Fine, this is length tension relationship graph. So what is basically physiology behind it? There is, whenever we stretch the muscle fibers, the actin and myosin component, the number of linkage between them, first of all they were overlapped. When we stretch them further like this, so the number of linkage between these two increases. Fine. So here with increase in length, the number of linkage increases, and because of this region till here the tension was increasing. This tension was increasing because previously they were overlapping, and when we stretch this muscle, there were number of linkage were more, right? At this point the number of linkage were maximal, right here, and that's why we have maximum tension. And when we further stretch, they were obviously they will be pulled apart, and that's why the number of linkage were least, and that's why there is decrease in tension. Got it? So this is length tension relationship, which you can be asked in your exam, separate question, length tension relationship. So you have to explain this physiology, why tension increases previously, and then within physiological limit. You know now why we are writing physiological limit, right? So maximum tension when there is maximum number of linkage. With further stretching, the number of linkage reduces and tension reduces. Okay, so this is last property of cardiac muscle. So in this video, we have discussed all the properties of cardiac muscle. We have covered morphological properties and the metabolic properties. So you can leave metabolic properties if you want, but these two segments are very important, and how you have to explain. We have touched upon every point, how you have to explain all of these. So I hope this point is clear. If you have any query, you can comment below. Thanks for watching.